should say I really appreciate all of you waking up for the IT school.
But
I understand weekends are precious, and so I'm sure this weekend will be memorable and fun. Anyway, I read something to introduce Robert Coltrane. He is, again, he needs no introduction, so I don't have to tell you all his accomplishments, but there's some in particular that I'd like to bring up. He's a member of the NAE. He has won the FaceTime Award, which is for mentoring, a presidential award for mentoring mentorship in science, engineering, and mathematics. And he's mentioned to me, which is, I think, of great value, which is he's mentored a lot of female students as well as faculty members. So he is, there's a lot to learn from him, not just about stationary course, but also on mentorship. He is at Stanford University, and he has won the Jack Kirby Award as well as the Shannon Award. So both in signal processing and in information theory. So it's a real pleasure to have him. He's also one of my teachers, so I love him. So it's an added pleasure to have him in our presence. Thank you very much, Rob, and we look forward to hearing.
Thank you. Good morning. I'd like to begin by thanking Sriram and the organizers for inviting me. I have to say, I think this is the first time I have ever in my life given a lecture at 8:30 on Sunday morning. I'm extremely appreciative that if I had to get up at this hour, you were willing to do so as well. The topic today is sort of a minority position in information theory, I will admit, but I think there are many ideas and techniques and tools that come with it. There are also some really cute examples that violate a lot of people's intuition, things that certainly surprised me when I first encountered them. So I think they're useful to sort of warn you of some of the pitfalls that can crop up in information theory, where you might think that things are a bit neater than they are, or it's easy to decide what kind of a process you're looking at. So the hope today is to sketch a bunch of these things. I may wave hands about a couple of proofs, but basically I'll be avoiding the proofs to talk about the results, and I hope it will provide a different view from the one you have almost certainly gotten in your basic information theory classes. And if you're new to information theory, I will try to say a few words about the fundamentals when necessary, because it never hurts to do a little bit of review before going into things. And all of you know who Shannon is. How many of you have ever even heard of Don Ornstein? Well, good. That's actually a bit of a surprise. He's somebody I think information theorists should know about, because he did things with Shannon's ideas that solved classic problems in probability that people have been trying very hard for a very long time to crack, and he did it. And the way he did it, I think, has something to say about information theory. So that's part of the story. There'll be a bit of meandering, I confess. It's not going to be exactly a logical order of things, but just to tell you what I'm going to do, or try to do, in the first part, is I will try and present as a guide for my meandering coin flipping. When you're a probabilist or an information theorist, you don't need a lot of equipment if you want to start simulating some simple, basic, but very important processes. You probably all have a coin in your pocket. You can pull it out and flip it. Most people discount coin flipping as being maybe too simple. You use it for the beginners, the debutantes, and very quickly move on to more advanced stuff. And I'd like to show you how sometimes you can get there by simply doing things with the coins, specifically by putting them into a stationary code, which I'll tell you right now is basically just a filter, except it may be nonlinear. But it operates like a filter and not like the block codes most people learn about in information theory. So I'll be doing some contrasting and comparing of the two coding structures, but the focus is going to be on the stationary codes. And the others, just to point out that I'll talk about entropy, which most of you at least think you know a lot about, and I would like to point out some oddities about it. Process distance measures is something that some people know a little bit about. Professor Mitter talked about it briefly during his talk, and I share his opinion that these things are really of fundamental importance. They've been around for a long time, and so it's one of the tools I'll emphasize. And then the optimal fakes, just to fill it in before we actually get there, say I give you a coin and you get to flip it. And you get to do something with this sequence of coins, and what has to come out is something that is going to fool people and think it's an IID Gaussian process. And I mean by fool them, it'll look like it if you draw a picture of it, and if you say to somebody to try a, say, Kolmogorov-Smirnov test of Gaussianity of something, it'll pass. All right, so you can think about that a little bit, but that's essentially where we'll end up at the end of the day, is trying to figure out how to do that. What's the best you can do, and how do you get close? And a question that's really only been partially resolved in the last few weeks is, do optimal codes for that problem exist? Presumably we can define something as an infimum in some way of all possible, infimum of the level of badness of all possible approximations, but is it actually a minimum? Is there a best way to take coins and flip them and confuse somebody into thinking it looks Gaussian? Okay, so here's what we'll consider. And I sat down in the easy chair and tried to actually flip coins to produce the binary numbers. You may know if you try and invent them in your head. Most people do a very bad job of writing down random numbers, so it's much easier to just do it. And my argument is these things not only are useful for teaching basics and stuff, but it can actually form the core of a model for much more complicated processes. And I confess, as I begin, it's not going to look much like Shannon theory. It'll bring up some Shannon ideas, but it will really only be in the second part of the talk that I'll start trying to make the link with Shannon theory as usually understood more solid. Okay, so here's the basic idea. I've got coin flips, and whenever I write Z, I will usually mean coin flips. Everything generalizes really easily if instead it is some finite alphabet equal probable IID source. So I will occasionally have a capital R for rate, and by that I mean we've got something that's got an alphabet that's of size 2 to the R. But think R equals 1, that simple example will get us through most things, and when I'm writing it to say R, it's just trying to give a suggestion of how you can generalize easily, and there are more generalizations that take more work. So it's going to go into a box, which is a stationary filter, and the main idea is every time a binary symbol goes into that box, one of the xn's comes out. And so what you can think of is this G is some function, and I've got double dots on both sides. It's a little different if you're working with processes that start at time 0 or have been going on forever, and I'm going to try and avoid those issues. So the point here is that there's some location inside there that's got an n in it. That's the Zn that I've just put into the box, and then it's looking at the past and maybe the future as well. So the main idea is, if I want to look and see what the next output is, I take my entire input sequence, I shift it by 1 time unit, and then I apply this mapping G to it again. Now, without going a lot into it, this is a sliding block or stationary code, as opposed to a block code which would look at a chunk of the Z's, put out a chunk of the X's, throw it all away, go look at the next chunk of Z's, put out a chunk of X's, and continue in that way. So a couple of times I'll stop to do a little bit more careful comparisons. And one of the nice properties of stationary codes is that if you put in processes with certain properties, you get out processes with the same properties. For example, if it's stationary, presumably everybody knows what that means. Ergodicity, which some people do and some people are kind of fuzzy on. Mixing, which at least probabilists know all about, and I'll mention what these terms are later, a little more carefully. K and B. How many people have ever heard of B processes? Okay. Oh, you're cheating, you're a faculty. How many people know what a K or Kolmogorov automorphism is? How many people know what the 0-1 law of probability is? All right, then you really know what K is. I won't go into detail on that, but these are just various types of processes which, if the input has that property, so does the output. And the point is, block codes have none of these properties. If you take an input, even if it's IID, and you code with a block code, you lose all these nice statistical properties, which causes a lot of contortions in doing information theory, because block-coded stuff is not stationary. There are various ways of making it stationary, but they aren't equivalent to actually using a stationary code. So I'll give a name here, which will come back from time to time. One question is, how big is the class of random processes that I can generate by using any G applied to coin flips, fair coin flips? And I'll call that B. B is for Bernoulli, and 1 because my alphabet size is just 2 to the 1. So if I wanted to be a little more general, I could have it B of 2 to the R, and then my alphabet size would be 2 to the R. So that will crop up from time to time. All right, here's an example. I've got a shift register of length 3. The bits are coming in from the left, and then G is just a table. And things are in blue really to set up what I'll do later. Think of it as the state of the shift register, where I've got a state which is the most recent 2 values, and then I will have a new input, and this is a finite state machine which will take the new input to state and go into a new state and output something. And here are the outputs, and those numbers might look kind of odd, but note they're not binary. They're a collection of real numbers, and to tell you where they come from, I'll do that later, but I'll mention the intent here was to try and imitate a Gaussian zero mean variance 1 random variable. All right, you can hopefully say obviously, but you can't get a Gaussian 0-1 variable out of coin flips, and that's true. And the question I'll ask shortly is, well, if you can't get it exactly, how well can you do it? All right, so here, and let's see if this works. Ah, it's not. So let me, Adobe, oh, there we go, it's working. This was done last minute. The bits are coming in from the left, they shift through the shift register, and you can see what's coming out on the right. And the only point of this was it's really important to understand what a stationary code is before I proceed. That it operates in this one symbol in, one symbol out way, and clearly what is coming out can have an alphabet different than what's coming in. And since it looks like a filter but possibly nonlinear, I can build examples by considering linear, and I will consider nonlinear of particular types. Okay, so that animation, unfortunately, neither my student nor I could figure out how to get out of it, except to go back into Adobe Reader and force out. Okay, when I build a code like this, it's got a certain structure. For example, when a new bit comes in, I've only got 2 new possibilities of what I can do next. They're forced on me because the other stuff in that shift register is the state, and that's already there. So I can draw a nice picture of what's going on at the output of such a code using a diagram well known to information theorists called a trellis. It would be a tree if the shift register has an infinite length, which I'll allow in a moment. So here's a picture which I'll revisit later. The idea is you've got the states, which I told you about. Those are the nodes. And then the transitions are dictated by what the new symbol is coupled with the state. You will go from one state to another state and output whatever the G function is. So it's a directed graph. It's a structure that's on the output of anything that's created in the way I've done here by putting coin flips into a stationary code. And just as an observation, which will matter from time to time, if I pick these G's to be distinct, if the input triple is distinct, and that's allowable, and probably a good idea, because if I'm trying to have a big class of stuff, I don't want to waste information by repeating these G's. If I pick them to be distinct, then a little bit of thought will show you this is invertible. That is, if I give you the output of those filters, you can just look at this picture and tell what the inputs must have been to get you there. And that's kind of nice because it tells you whatever I'm producing has certainly not lost information in any intuitive sense from what went in, because I can recover what went in from what comes out. All right, invertibility will crop up on occasion. Here's another example just to show you that this is a model for a binary autoregressive or binary symmetric Markov source. And I do it by taking the inputs, having some feedback, doing a mod 2 addition, and my output looks like the thing on the right. And so one point is I could use a linear. Here is GF2, it's mod 2. And again, this ends up being invertible because I just write down this formula and I can invert it with another mod 2 linear filter. So I might want to have binary in, binary out, and I can build a bunch of processes that way. Now this gets a little more interesting. I can put in a convolutional code, but using real arithmetic. This is an idea that in source coding goes back decades. So you start with binary, but your convolution is really with the real alphabet. Well, that's just a linear time invariant filter. But I'm going to pick a particular one. I'm going to use a geometric filter and just have it decay. I also need to throw in this finagle factor, the scale in front. And I get out this sequence of random variables which can now take values in the unit interval. In fact, it can take any value in the unit interval. This is just the binary expansion of a real number in the unit interval. So I have now gone from coin flipping to a sequence of random variables which have a continuous alphabet. And this is going to play a little havoc when you start trying to do elementary information theory. What kind of a process is this? Is it continuous? Is it discrete? What can we say about it? Well, one thing I can say that without proving, hopefully, is it's not too hard to show that if these things are equally likely, then that UN is going to have a uniform distribution on the unit interval. So I've taken coin flips and I now have a uniform distribution, a sequence of things, each one of which on its own has a uniform distribution. Now one point here is that unlike block codes, it makes sense for me to talk about an infinite length code. A block code it doesn't, because you look at longer and longer blocks, if it's an infinite length, you've got a sequence. So an infinite length sequence would map the sequence into a sequence and you're done. There's no notion of dynamic coding, of repeating the blocks one after the other. But with this, it's perfect notion of dynamic implementation, because I just keep shifting the input and I keep getting outputs. Okay, this one, just if you do a little algebra, it turns out it's invertible as well. You can recover the input from the output. So this is just observing that I can take coin flips and I can try and fake the output of rolling a die. I can have an alphabet with 6 things in it, or I can have a continuous alphabet. I just told you about 0, 1, and next we're going to look at the real line. So I've got quite a variety of things I can do with this. Now is probably a good time for detour 1 on stationary codes versus block codes. Just again, this is really for people with a minimal information theory background, because the assumption is people with a good information theory course already know about block codes. So this may not hurt, because at least it is a good reminder and a contrast. So if I talk about coding something into something else, and right now I'm not specifying if it's channel coding, if it's source coding, or if it's trying to code in order to build a model of a random process. Just taking one thing and coding it into another. The block coding I described already, that's the standard in information theory. The stationary coding I've also described, and that's the standard for a technical area called ergodic theory, and I'll define that shortly. But that's the one in which Don Ornstein works, and that's the one I'll be trying to tell you some stuff about as we go along. And here's graphically the picture of what I wave my hands to do, and now you can see what it actually looks like. It's taking blocks to blocks where it's sliding a block along. And later I'll just do some mentioning of actual codes that have this form that are in existence. And you all know lots of codes that have the top form. And oh, the bottom comment I should make. both of these coding structures will take an infinite sequence and map it into an infinite sequence. And when we start getting a little bit abstract in trying to write some general results, it's often good to look at what it's doing to the sequences, not just what it's doing locally. All right, back to coding coin flips. Remember we had the linear time invariant filter and I got something that's uniform. All right, now you can play the elementary trick that's taught in most probability courses. If you have a uniform distribution, how do you get any other arbitrary distribution, say Gaussian? Well, you use the inverse cumulative distribution function, and that's obvious in definition if you've got something that's monotonically increasing for your ideal CDF, like the Gaussian is, and then you have to take a little more care otherwise. But what I will do is take that uniform thing, put it through the inverse CDF of the marginal density, the density on the real line that I want, or it's CDF here, and that will be my output. And here is just a comment I'd like to throw out that I find kind of curious. This has a particular structure, this code. It has a linear time invariant filter followed by a memoryless nonlinearity. That turns out to be a special case of a class of nonlinear systems that have been studied, never in information theory to my knowledge, but in control and systems, where you model you limit yourself to a class that's got a linear time invariant filter followed by memoryless nonlinearity, because you can often handle those, followed by another LTI. These things have a name. They're called Hammerstein systems. And the codes that I will end up in part 2 talking about that worked really, really well for IID sources end up having exactly this form. So I suspect when you're trying to get nearly optimal source codes that are stationary, they're going to end up having this form. And is that true or not? I have absolutely no idea. And I don't know if that connection is really good for anything, but I think it's worth pointing out. Might be. Alrighty, so now we've generated a process. We've got Gaussian marginals on the output driven by coin flips. Is that a Gaussian process? How many think it is a Gaussian process? How many people think it is not a Gaussian process? How many people are unwilling to declare either of the former two? Okay. All right, the answer is no. And a couple of ways to view this. The best way we'll get to in a few slides. But one way is if you look at conditional distributions of this for what is the distribution of what happens next given what happened last, it's discrete. So that can't be Gaussian, because if it's Gaussian, everything's got to be Gaussian. This is the simplest way, though. Do a scatter plot of adjacent samples. That doesn't look like an IID or any other kind of Gaussian. That looks like if you know one sample, its correlation with the next sample is very high. All right? So that doesn't work. The box up in the upper right, that's because I'll use this later. And so ignore it for the time being. Okay, that's not a Gaussian process, and we can decide that fairly elementary, but now I can tweak it. Let's take the coin flips as we did before. F is my CDF of the normal. But now I throw in this funny thing I'll call a scrambling function, which just maps the unit interval into the unit interval, and it has this symmetry property around the center. But anything that has that form will work. And now I stick that in between these uniform things and this CDF. So if you like, this is going to take the uniform random variables, which we've seen are just really highly correlated, have a lot of memory, and try and scramble it all up, mix it all up. And that gives me this new process. Now it turns out this new process is more interesting than the last one, because now it's easy to show that Xn has Gaussian marginals and it's uncorrelated. So I've got uncorrelated random variables with Gaussian marginals produced by coin flips. So is this a Gaussian process? Okay. How many people think yes? Ah, you've been burned. You're cautious. How many people think no? Okay. And how many are still refusing to declare? Okay. So the answer, and it's not as obvious as it was before, except the people who really know information theory will have a reason handy, and we'll come back to that later. It can't be. So, does anybody know why? I mean, other than just the intuition, can somebody give me a fact that could be, that rigorously says this can't be Gaussian? Okay, let's. No, I'm not going to ask you anything. Yeah?
The entropy
Right.
is the same.
So we will come back. So one thing is the way to make decisions like this about what kind of a process we're looking at is going to involve the entropy quantity of Shannon. Even though it doesn't look like we're doing information theory yet, it's lurking. And so we'll get there. And that's the rhetorical question here. Nothing I've said so far would really make what I've done or talked about relevant to a school on information theory. So I still have to get there. So what I can argue at this point is I've raised some issues about how we would classify different kinds of random processes. And we've seen some simple properties. Entropy and entropy rate is going to play a big role in that. Stationary codes are the common theme. And then when I start trying to answer questions like, if I use coin flips to pretend I've got a Gaussian, what's the best I can do? I'm going to need to quantify the notion of best. So that leads me to ideas of distortion and distance between processes. Here's one process that may look like a Gaussian. Here's another one that really is. How good is the fake of one of the other? How do I measure precisely and quantitatively in a useful way for information theory how close one process is to another? So if I can't get 0, maybe I can get epsilon close, which would be good. Modeling versus compression, that will be trying to tie what we're looking at now, which is the modeling or the simulation, with the actual Shannon theory applications, which are going to be the source code. And I should mention I'm also a minority information theorist, as my main interest is source coding, but stationary codes are still of interest, and there's a literature for them for channel coding as well. It's just that that's not the main theme, or not the theme at all here, and it's not my main interest. So it's source coding that I will be going towards. All right, so that sort of just says what I said already. I'm going to try and do a sketch and a tour of some of these ideas. Okay, first, when I'm talking about an information source, like Shannon, I just mean a random process. But I'm going to need to take the view of a random process as a probability distribution sitting on a sequence space of possible outcomes forever. This is the Kolmogorov formulation, and Kolmogorov will crop up later because he's really the one who realized that Shannon's entropy could be used for a lot more things than just for lossless coding theorems. And in order to make sense out of some of those definitions, we have to take from time to time the process overall view of things. So I will, when I tell you I've got a process, I will assume I have some process distribution, which will just have the single letter there. And what that means is this thing that exists, at least in the abstract, as a probability measure on all possible sequences. So the other thing I'll mention is that measure sits on the probability space has to have a sample space. I've got it. It's got to have an event space, which technically is a sigma field. And I'm just going to say I'm assuming that I've always got those sigma fields without having to tell you what they are, that my functions are all required to be measurable, and all of those measure theoretic details, which I don't want to mention again unless you have questions on it later, I'm going to shove under the rug. So I'm just going to take the general viewpoint. It's a probability distribution on a sequence space. Now I am going to allow the processes I look at to have a discrete alphabet, or maybe not. And the maybe not is a hedge. It's not a question of just discrete or continuous, but there are things which are really not quite either. They're clearly not discrete, but they're not really continuous in the sense of continuous meaning you've got a nice, well-behaved probability density function. So I'll just say discrete or not. I need definitions that work when I can't write down a PDF, and there's not a PMF either. Another thing that crops up in this is the idea of the shift. This is the way that the notion of time is captured in dealing with these kinds of models. And the shift takes an infinite sequence and moves it to the left by one stage. So here the picture is whatever was in position n now is occupied by what was to its right before. So it just shifts it to the left. Now, a dynamical system in ergodic theory, so you're learning a little bit of ergodic theory. In dynamical system, that name was in ergodic theory long before it got adopted by the systems people. It is just this collection of the probability space, the probability measured on sequences, this shift transformation which moves things, and a random variable. That is, the random variable which looks at the entire sequence and prints out whatever is at the 0th coordinate. Now you get a random process from a dynamical system. If you want the nth value, you shift the input sequence n times and then print out what's now at time 0. I'm not going to use this a lot, but this is to try and give you a feel for the fact that t is just a way of capturing time, and that this is actually a generalization of the idea of a random process, which, again, I'll stick to random processes. But you've got this more general idea because you can put a transformation on lots of spaces that aren't sequence spaces, or you can put things on sequence spaces that aren't shifts, and still generate random processes from them. So that's about as much ergodic theory as we need for basics. Stationarity, you all know that it means if you shift an event, the probability doesn't change. And now with the notation I've got, I have a simple way of writing it. Shifting an event is taking the inverse image under t. That's just set theory. And if that doesn't change, then what I have is a stationary process. Now I will focus on stationary processes, but when I list the taxonomy, I will also list some processes that are not stationary but can be handled with more work and more notation by using very similar ideas. So I'm emphasizing, but I'm not saying it's necessary. In ergodic theory language, instead of saying a process is stationary, they say that t is measure preserving. Because if you look at that, it says that when you use the transformation t on a set, the measure you get is unchanged. So it preserves measure. Now I can tell you what ergodic theory is. It's the theory of measure preserving transformations. So for us, it's the theory of stationary processes. But I have to throw in, it's also the theory of related transformations or related processes. For example, things that aren't quite stationary, but if you let things settle down, they will be. Processes with initial conditions, block stationary processes, asymptotically stationary processes, and a class of things called asymptotically mean stationary processes. These are basically all of those processes for which relative frequencies and sample averages converge to something. Might be a random variable, but they converge to something. And that's basically the generality in which classical information theory at least makes sense. Now, ergodicity, the definition of that, engineers usually don't get in their basic probability courses. So I'll just mention it, and then I'll give you a somewhat more intuitive equivalent definition later. But the definition, you don't need stationarity. It just says if I have an event that's invariant, what would that be? Well, it would be the event, for example, that the relative frequency of points landing in the interval 0, 1 converges, and maybe it converges to some value, or just converges in general. If I shift the sequence, it doesn't change that. So that's an invariant event. If it's ergodic, invariant events have to be trivial. They either have to have full probability or no probability. So that's thrown out as a definition. It has lots of implications, especially when you add stationarity to it. And here I'll just mention my emphasis, and the emphasis in the literature is on things that are both stationary and ergodic. All right, while I want to look at sequences, just when you're actually computing stuff, you may want to look at vectors again. So if you've got a sequence distribution, you have all of the vector distributions. Kolmogorov tells you that if you have a consistent family of vector distributions, that implies a sequence distribution. And that's taught in a lot of engineering random process classes. So people know that if, provided the probabilities are consistent with each other, there is this measure out there on sequences. You just can't write it down in an easy way. All right, IID sources. These, I argue, play a fundamental role, and part of my point is to show you how fundamental, and that's actually one of the major points of ergodic theory. So I would argue these are not only useful as a beginning example, but they're useful as a way of constructing probably the class of all processes about which engineers should ever worry about. If it's more general than that, you're probably never going to encounter it. But for the moment, I'll just say IID, continuous, discrete, can't decide between the two, simply means that I've got any vector distribution is a product distribution, so the things are independent, and the marginals are all the same. So it's like coins or rolling dice or IID Gaussian. IID processes are arguably the most random of all possible processes in that there is no prediction there. And this, with apologies to Rich, who will be talking about compressive sensing later on, these processes have no sparse representation. There is no way you're going to make any use of compressive sensing on a process like this. In fact, often the point there is to end up with a process like this. So this is really my focus. A bit of nomenclature, if you read the literature, this has driven me and several friends nuts. And so if you do go, just be warned about how the name Bernoulli is used. In information theory, it almost always means, when you hear Bernoulli process, it's binary, it's IID, and it's got some parameter p. So my main interest here is the parameter p is a half, so they've got a fair coin. In ergodic theory, they talk about a Bernoulli shift, not a Bernoulli process, and it means that, in our language, it's an IID process, but not necessarily binary or even discrete. The trouble is that nomenclature is not everywhere. There are divergences in two ways. One way is that some of the literature restricts Bernoulli shift to finite alphabet, and then we'll call what I call a Bernoulli shift a generalized Bernoulli shift. And I always get a little annoyed when people start tacking the word generalized on front of things instead of just defining them more generally. It's excess verbiage, and I think not what's usually done in the literature. What you have to watch, though, is that some people, instead of meaning just finite alphabet, mean that a Bernoulli shift is not only things that are IID, but things that are isomorphic to IID. How many people know what isomorphic means? With comfort, right? I won't challenge you to tell me. I'll just point out that this is a new word, so I should, in all fairness, define it. And we can't. It just says you can, with a stationary code one of those processes into the other in an invertible way. So you can recover the original process. So it's like most of those examples that I showed you. All right? Some ergodics theorists use this general notation, general language, because they basically think the two processes are the same if they're isomorphic. But to an engineer, that's not quite true, because we may have our binary coin flips and want to get something else out of it, and we're going to be concerned about how to do it. Ergodic theorists, like engineers, often have things that are either existence proofs that these codes exist without telling you how to do it, or they tell you how to do it with a construction that's absurd computationally. I mean, just be completely unreal. But whatever, isomorphism is sort of like a Shannon noiseless coding theorem. You can take one source and code it into the other and come back, at least with probability 1, perfectly. The difference is that here I am allowing continuous things as well as discrete things. And that's not something that information theory courses usually take into account. So let's look at an example. If I take an IID Gaussian and I put it through a simple geometric filter, causal, and I get out the Gauss-Markov process, I can filter it, that's the Kronecker delta, and recover the original perfectly. So those two processes, in ergodic theory terms, are isomorphic. But you would not see it referred to as a noiseless code because things are continuous on both sides. Now, note also here, I am generating something by taking an IID process and putting it through a stationary code. And I've got something new out of that. Well, you might complain that this isn't really a code because the output doesn't have a discrete alphabet. So you could call it in this case, just a linear time invariant filter. And that would be okay. But I'm going to interpret it as well as a stationary code. Okay, B, that was one of the processes people didn't know about. Easy to define. It's the class of all processes that you can generate by stationary filtering an IID process. Okay, that means it's got to be stationary. The input has to be IID. It does not have to be discrete. So this is a bigger class than that B of 1 or B of R that I described for you before, but that's on purpose. This is Ornstein's class of B processes. He has used that name, and lots of other people, unfortunately, have called them Bernoulli processes, which means an information theorist reading this literature for the first time is going to get a little confused, because this is not, your grandmother's Bernoulli process. So, question is now, where do these things fit in? And here's a taxonomy, which lets me say a few words about generalizations and then not say any more after that point. Okay, IID I'm considering as my core. This is the most narrow possible class, which I'm arguing is still important. Clearly, I could use as a stationary code an identity mapping and just get the thing back. So that's a subset of the class of all B processes. And B processes sits, though, next to IID. At its core, are IID processes such as coin flips. That is contained in the class of K processes. And I guess the main point is nobody really has any description of any good and interesting class of processes between those two. Now, usually when people have seen the 0-1 law, which I don't think I'm going to spend my time explaining, I'm having to do it offline. But when you've seen it, it's been proved for IID processes. However, you can define a more general class of processes than IID by just saying everything that satisfies the 0-1 law. Okay, so B is contained in K, and then K is contained in strongly mixing, and that's defined down here. And it's sort of an asymptotic independence property, but it says if you take any two events and you start shifting one long into the past, then eventually that's going to look like the product of the two probabilities. So if you like, things are asymptotically independent as you go into the distant past. Now, sort of a nice idea, because then you can generalize that slightly. Instead of trying to force this happen on its own, you can have sort of a mean of absolute values. So that's weak mixing. And then it turns out if you're dealing with stationary and ergodic, which I'm assuming here, that is, my strongly mixing and mixing, as is usually done, are also required to be stationary. They will be ergodic, that's automatic, if they're stationary. An equivalent statement for ergodic is this, and this is sort of an asymptotic mean variation of the asymptotic independence. So ergodicity is best thought of as a form of asymptotic independence from the past. Like mixing, like strong mixing, but more general. Okay, so that's contained in the stationary and ergodic, which I will consider often as a general class. The things in blue are just the things I'll most often talk about. That's contained in stationary and block stationary and asymptotic. I've mentioned those other things, and then the last one is really has something to do with when the ergodic theorem holds. The general version, where just relative frequencies and sample averages converge, but they don't necessarily converge to a constant or to the probability of something. Okay, so I'm going to focus really on B, on IID, and stationary ergodic. And that was my, this is just a reminder to me, to remind you that our binary, our coin flips through the stationary code is just sits in the class of B processes. Now, in ergodic theory, I think you can say B processes are the most important of all, and I'll tell you why shortly. And I'm just pointing out, I think they're of interest in information theory as well, as a model that's actually quite general, and ergodic theorists would tell you that it models so much stuff, it's almost certainly to include most reasonable physical phenomena that you are likely to encounter. Oh, what I should have said and didn't. If you have something that is stationary but not ergodic, then there is a way to handle that. There's a thing called the ergodic decomposition that tells you any stationary source has to be a mixture of ergodic sources. That basically says that nature uses a probability distribution at the beginning of time, selects an ergodic source and sends it to you. So what that means, if you say it's stationary and not ergodic, it's just you're ignorant. It really is ergodic. You don't know which ergodic component you're looking at. But in information theory applications, you can usually take your stationary ergodic results and extend it to stationary non-ergodic using that ergodic decomposition. If you throw away the stationarity property and get into one of those asymptotic versions, then there is an associated stationary measure, which you can write a formula for, which has all of the same sample averages and all of the same relative frequencies that your non-stationary thing has. So there are also techniques to handle that. So it's not that I'm just trying to avoid that stuff because there's something fundamentally different going on. I'm just saying if you can handle stationary and ergodic, you can handle, they're not magic, you can handle more general stuff. All right, so to proceed, I now need to get into a couple of the tools. The first one is entropy, and I'll start off strictly Shannon. It's not the way you define it in an undergraduate information theory course where everything's assumed to be IID, but it is the way it's usually defined if you're going to allow Markov and more general processes. And then look at the Kolmogorov generalization, which a lot of people aren't familiar with, but I think is really pretty simple and pretty natural. In fact, even some very famous information theorists I met weren't really familiar with it. Here's the usual definition. You start by defining the entropy, the Shannon entropy of an n vector, and I'll write it both as a function of the random vector and as of the distribution. Both are heavily used and both are convenient depending on what point you're trying to make. And it's just the sum of p log p over your alphabet. This is for finite alphabet. This is for, well, for finite alphabet. You've got a PMF, it's all simple. That's the point I should make. Now, the entropy rate of a process, rather than a vector or a scalar, is defined as the infimum over all n, which, if things are stationary, is also the limit. And this is one of the things that I'll give you a warning about. A lot of people take this formula for granted, when in fact, when we generalize, it might not be true. We'll see examples. There are simple examples. And that's hopefully a supplement, if you haven't seen it, to basic information theory courses. So an example for our coin flip case is all the nth order entropy and the process entropy are all 1 bit per second. Okay? So that's something everybody should know. Now, in the general case, if you look at a vector and ask what the entropy of the vector is, the Kolmogorov formulation is, take your vector, which could be continuous, mixed, or anything really nasty. Quantize it. Quantize means take the mapping from that possibly continuous space into a finite space. Don't care how you do it, just quantize it. Any quantizer is then going to give you a finite alphabet random vector and use the Shannon definition. Take the supremum over all possible quantizers of all possible finite sizes. That's not too bad. Now, when entropy rate is defined, and this is critical, he did not then say take the limit of that because it actually doesn't work. It doesn't give you a useful theory. It gives you wrong results. What he said was take the Shannon entropy rate of finite alphabet things and now quantize those. And that can be just a simple quantizer, symbol to symbol, or do it over all finite output alphabet stationary codes. They both give you the same answer. So I'll take the second one. I'll take the one that does the supremum over all possible stationary codes with a finite output alphabet. Now remember, if I take something that's stationary and maybe has a really weird argument and a really weird distribution, once I have a stationary coding into something with finite alphabet, I have a stationary finite alphabet process I can apply Shannon. So that's the general definition of entropy rate. And here is an example. If you apply it to a Gaussian IID, the IID will give you the fact that as always the nth order is the same as the entropy rate. But now if you look at quantized Gaussians and you take the Shannon entropy and now you make the quantizer finer and finer, it just keeps growing and blows up. So the Shannon entropy of one Gaussian random variable is infinite, of n variables is infinite, of the process is infinite. Now some people will think, well, what about differential entropy? And that's another warning, is Shannon differential entropy has its uses, but it is not Shannon entropy. It doesn't have the properties Shannon entropy does. I mean, you can change it by scaling, you can have it negative, and it really does not have much to do with ergodic theory. In fact, I think I can safely say nothing. It does help in information theory when you're trying to compute some things. But trying to use intuition or theorems for entropy for differential entropy is really dangerous. There are connections. Go to Cover and Thomas, and you can see if you start throwing in the right scaling factors, you can come up with approximations that relate these two things. But entropy is the thing that's important here, not differential entropy. All right, entropy is important because there are two important results, which are unfortunately very difficult to prove. So I won't even try and hand wave them. I don't think you need to know the proofs, but knowing that these exist, I think gives you a good appreciation for random processes. So the first one is called the Sinai-Ornstein theorem, although now most people just call it the Ornstein theorem. It's famous because, well, for one reason, I guess, Sinai published this beautiful theorem. Everybody that I have ever talked to, ergodic theorists included, have said they have never met anybody who understood his proof. And so when Ornstein developed a very careful proof as part of the more important theorem which comes next, his name was applied to it, although he admits that it's Sinai's theorem. So I'm giving both names with temporal priority, Sinai. But if you want to learn about it, it's not Sinai you should read, it's the Ornstein you should read. What it says, I think, is really rather amazing. If you have two stationary ergodic processes, and process X has entropy, Shannon entropy rate, bigger than or equal to process Y, and these things can be infinite, then there is a stationary coding of X such that the output process has the same distribution of Y. So all you need is bigger entropy. So that suggests something possibly interesting, which actually people working for decades, is what if the two entropies are equal? Equal's allowed there. I could take process X and do a stationary coding and get process Y. Then I can take process Y and do a stationary coding and get process X. So I can recover either one from the other. So are they isomorphic? Well, that hasn't shown it. The isomorphic, you have to get a stationary mapping that's invertible. And that's not true in general for stationary and ergodic processes. That's where the next theorem comes in. And it basically says, if you have two processes with the same entropy, and they are both B processes, and then there's an invertible mapping from one to the other. So this is like a super analog to Shannon's noiseless coding theorem. Stationary codes, continuous sources, all of that. And it's what makes entropy so important to ergodic theorists, and it really tells you when two processes are genuinely different. You can't go from one to the other and back again. Recover your original sequence. It has been known for a long time, Kolmogorov and Sinai show that equal entropy is a necessary condition for isomorphism. The hard part was showing sufficiency. And in fact, necessary is pretty obvious just from our definition of entropy rate. That was the easy part. But this was the hard part. Ornstein's basic work on this is an entire book, although it appeared in papers at a short time at the end. I have references if you're interested in this, because there are some beautiful introductions that are absolutely understandable, in particular Paul Scheele's book called Bernoulli shifts. But Ornstein is dangerous to tackle without a good long run up to it. Now, not only does the isomorphism theorem work for B processes, that's the most general class of processes for which it's known to be true. If you go up to the class of K processes, equal entropy does not ensure isomorphism. And mathematicians have had lots of fun constructing uncountable numbers of K processes that have equal entropy and yet are not isomorphic. Okay, so I guess just the summary is if you got two B processes, you can go back and forth between the two if they have the same entropy. And just remember, IID is a B process, so that's going to help me when I'm trying to see how general my class of models is when I'm doing stationary coding of IID processes. Okay, so this is the other warning that I wanted to point out. Do not assume that the entropy rate is always the limit. And the simplest example I know of is a stationary random process can be constructed as follows. At time 0, just pick something according to a Gaussian distribution, and then set all other random variables at all other times equal to that. All right, you will then have a finite order entropy that's infinite for all orders, for 1, 2, all the way up. But if you check out the definition from Kolmogorov, the entropy rate is going to be 0. Because there's no new information there. If you know more about entropy, the conditional entropy given the entire past is going to be 0, because you know exactly what's going to happen next. And that's an equivalent form for the entropy rate. So that's a case where you can't trust the vector order entropies. On the other hand, that's of interest to me, because if I'm trying to fake a Gaussian process, I could have, without contradiction, a fake that's going to have infinite entropy and look very Gaussian over the short term. But eventually it's got to be discoverable. It can't go on forever. Okay, this is a bit of an extreme example because I just repeat myself. It is a stationary process, but it's not ergodic. So maybe it's somehow rigged and you don't have to worry about this. And this kind of brings me back to the fake white Gaussian process that I created. That's a stationary process. It's an ergodic process. It's a mixing process because it's a stationary coding of an IID process. I created it from coin flips. And as I said, it wasn't Gaussian, and the gentleman in the audience correctly pointed out it was entropy that would give the game away. And here I've created a fake process that has vector entropy that's infinite for all n. It's stationary ergodic, it's really nice. But it's a stationary coding of something with 1 bit per symbol entropy rate. And stationary, remember, entropy rate's defined as the supremum over all possible quantizations of whatever it is I get. But they're quantizations of a stationary encoding of a binary process. Stationary encoding must reduce entropy rate, because entropy rate was the supremum over all possible. So I can't have any more entropy rate coming out of a stationary filtering of something with 1 bit than 1 bit per sample. And that's something you can't see unless you know Kolmogorov, and unless you know it's entropy rate, not finite order entropy, that counts. So my process was a fraud. It has entropy rate 1 bit per sample, or at least no greater. So maybe it's a good fake, but it's not Gaussian. That gets me into the question, oh, okay, it's not Gaussian. How good a fake is it? And that brings us to the topic of distance measures on processes. And I'll start out simple. I want a way to measure how good my fake is of the original thing. And so I'm after a way of putting a distance, maybe a metric. I mean, these words are used mathematically and they're used loosely. So I'll say distance when I mean sloppy, and I'll say metric when I mean it's got the triangle inequality. And it's symmetric, which I really don't care about that much. But generally what I want is I want something that's, if you take the distance between anything and itself, I get 0. And if I take anything that's genuinely different, what do I mean by that? I mean, if you look at the probability, some of them are going to be different on different events. It's not the same process. Then I want to have strictly positive. All right, so I'd argue that just to start with, these are reasonable things to require. I'll get more specific later, but this will already give me something. Because basically it says if two things, if they're the same, I get 0. If they're not the same, it's got to be bigger than 0. The notation, by the way, is d bar, and that's because I'm borrowing from Ornstein, because he's really the one who came up with the process distance for a particular case. All right, so that gives me a way to define the best fit. If you give me some class of processes like B of 1 or B of R, then I would like to find the infimum over all sources in that class of the distance from my target process, mu x, to my take. And I would just use, this is pretty standard when you're dealing with real analysis and distances, the distance of a point to a set. My point is a probability distribution. The set is the collection of stuff. It's just the infimum of the distances from the point to the set. So I'll call that my optimal fake if the infimum is a minimum, and I may slip up and say that, but I can get arbitrarily close. I may use optimal when I'm not justified, but I can get really close to it. All right, if I pick a process that's in my class of everything I can generate, let's say R equals 1, from coin flips, then I know that the entropy has to be less than or equal to 1. So I know the distance from my source to that particular collection of stuff. This is just meant to give you a graphical picture. I'm really optimizing over all stationary codes of a coding of binary coin flips. That is going to be bound below by the distance from my mu of x to the collection of all possible B processes. I mean, this is a B process, so I'll go over all B processes that have that constrained entropy. And that's got to be bound below by the distance to the class of all stationary and ergodic processes with that entropy. So I've gone successively more general. And so the natural question is, are these inequalities equalities? And the answer is, thanks to Sinai Ornstein, yes. Because essentially, waving hands, if I have the process and it's got the constrained entropy, I know anything that's got entropy that's bigger than or equal to that can be used to get a stationary coding into the second process. So anything you can get that's stationary and ergodic with constrained entropy rate, you can get out of a coin flips if we're dealing with constrained entropy rate 1 and a stationary coding. So that's just a little bit of manipulation, and I'm shoving the hard part under the rug, I admit it. This Sinai gives us this, and it's not something that comes out in the information theory literature. So what it essentially tells me is I know that the distance, this process distance, without having completely defined it yet, to what I can get out of binary coin flips is equal to the process distance to the much more general, the much bigger class of all stationary and ergodic processes with a constrained entropy rate. So that's pretty nice. That says, at least in theory, if it's stationary ergodic with entropy h, I can get it out of coin flips or rolling dice or something that's got enough entropy, but it's still IID. So I can get really close with a B process. Okay, that tells me that if I've got an entropy rate less than 1, strictly less than 1, I can get it perfectly. So I've solved my problem just because I stole what the isomorphism theorem said, or the Sinai Ornstein. Don't have isomorphism, don't have invertibility here yet. So the question happens, what if the entropy rate's too big? For example, R is 1, and the entropy rate of the source I'm trying to fake is Gaussian. Then I can't do that. So here's some questions based on what I have said so far. What's a useful distance measure? I have to come up with that. Can I evaluate the best fake when the entropy is bigger than my constraint R? Can I actually achieve it? Do optimal codes exist? Okay, they exist when I can do an isomorphism, but what about more generally? And here, somewhat surprisingly, is the answer is going to be no. That they don't exist. There's sort of like a discontinuity between ergodic theory, when you get things perfectly, and the information theory side, when you're willing to accept some distortion there. But we'll see that later. Okay, key issue I'd like to go through, that will be in the second part of what can I say about good codes? What are their properties? The reason being, I don't have a way of constructing them, but if I know how they behave, maybe I can come up with ways that are designed to meet those properties, and they'll do pretty well. And that actually ends up working. And it's a well-known practice in code design in the past. And then back again, I still haven't told you anything about where Shannon comes in all of this. And so I still haven't gotten really into information theory. Okay, here Professor Mitter talked some about this, so I don't have to, I'm going to go through this a little bit rapidly. But first of all, there are at least 100, according to a count of somebody who collected these, measures of distance and distortion and metrics on random processes. So you could just go out and pick one, but I want one that is particularly relevant to information theory applications, also ergodic theory applications, because some of them are so similar. So the one that I will pick, unfortunately, has been rediscovered so many times in so many ways, it's hard to assign one name to it. So I guess the shortest one that captures most of the key ideas is the Monge-Kantorovich transportation Wasserstein-Ornstein. Actually, there was also Levenshtein in there. The Brushin once joking said, because it was Ornstein, Levenshtein, and somebody else who I think had Stein at the end of their name, we should just call it the Stein distance. And then I found out about Kantorovich, whom the Brushin hadn't known about, so far as I know. And then Monge goes back to the 18th century. So this is an idea that has been around for a very long time. It was also rediscovered in the 90s in the computer science community as the Earth mover's distance, which doesn't sound that different from the transportation distance. So a little notation. I need the idea of pair random processes. Think of input and output. So that's just a pair of two things. I've got a joint distribution on the pair. That gives me the marginal distributions for each of the individual things. You can think of a box that produces the two, out of which I can get either the input or the output. It's not always input and output, though. Just think two processes. I can do the same with vectors. With vector distributions, because remember, if I've got a process distribution, I've got all these vector distributions, and vice versa. So that's just, if you want to do a communication system, you can think of it in that way. All right. I will assume for simplicity I've got real alphabets. That covers most of what I need. I need from information theory an idea now, and that is of a family of distortion measures for vectors of various sizes. And Shannon called that a fidelity criterion. And I'm going to assume an additive fidelity criterion, sometimes called linear, sometimes called single letter fidelity criterion. You just take the distortion in each one of the coordinates and add them up. Examples are the squared error and the mean Hamming distortion, which are well known to information theorists, and in fact those are the two most important for most of the things I'll say. Average distortion, you can do it for vectors, you can do it for a limit as n goes to infinity. That's the usual information theory way. But because I've made everything stationary, this gets simple. If everything is stationary, when you look at the vector average distortion, because it's additive, it's just the distortion at time 0. So I have this nice single letter characterization of distortion. One of the advantages of working with stationary stuff. Okay, here's the distance as Professor Minner defined it for vectors. I will look at all joint probability distributions that match the two vector distributions you've given me. And of those, I will find the one that minimizes the average distortion between the two. So here's process 1, here's process 2. I find a joint distribution. They exist, for example, you can make them independent. So there is such a joint distribution. But find the one that makes the expected average distortion between the two as small as you possibly can. And that is the transportation, or Kantorovich. And Kantorovich is worth mentioning in this because he won the Nobel Prize for economics. And it was for his development of linear programming, of which this distortion measure played a part. And one of the references I'll mention shortly has something like 700 references, books, papers on this distortion measure. It is really well studied in lots of areas of mathematics, and it's not been that much used in information theory. It has been used, but I think it deserves a bigger place. I'll mention in passing again, without belaboring the details, an immediate question is this thing really a metric? Well, it depends on what your D is on the per symbols, because if you pick squared error, that's not a metric. But if I take an average vector distortion using squared error, and then I'm all done, and I take the square root of it, that is a metric. So what this says is that if you have a distortion measure that's any power of a metric, then you can get a, if you like, transportation distortion by just leaving it alone, but it doesn't have the triangle inequality, or a transportation metric by taking the root, or not. You take the root if the power is bigger than 1, which is what most people deal with, because that's the LP norm, or as usually understood, but you can also have p that's less than 1, and then you don't want to take the root, and it's automatically a metric. I guess the other thing to mention here is if you take r equals 0, then people consider that the Hamming metric, not the average Hamming metric, but the 0, 1 metric, depending on whether the vectors are equal or not. So anyway, I will often say transportation or some other distance, and the point is you can get a distance out of it if you maybe take a root when you're all done. All right, this was the list of people. Volani is probably the best modern person to see. He writes very readable books. He, within the last year, won one of the major prizes in mathematics. I forget the Fields Medal. Fields Medal. Thank you. Anyway, his treatment is great, and for details, just go there. The process transportation distance, or this is what Ornstein first came up with, because processes I have not seen crop up in the transportation literature, is just take the supremum over all block sizes of that. Okay, same argument, you can get a metric out of that if you want, and all I'm going to care is two cases. If that's the Hamming, average Hamming distance, in which case I'll have a subscript 0, or if it's the squared error, in which case I'll have a subscript 2. Hamming distance is good for discrete. Squared error is everybody's favorite if you're dealing with continuous. Okay, some processes of this. And I may go 5 minutes over my 10 o'clock to catch up a little bit from our late start, just to get as much through the distance as I can. So the first thing is, if processes are stationary, then you can write the distance as an infimum over all stationary process distributions, which agree with your marginals, and just look at the distortion at time 0. Again, things are additive. It turns out also, if you have these processes are ergodic, then you only have to look over ergodic joint distributions. So it's got some nice simplifying properties. This is probably the key one. This says if I have two processes that differ by epsilon in the d-bar distance, what that says is if you take a sequence of one of them that's typical, in the sense that if you read off relative frequencies of a large number of events, you get what the probabilities of those events should be, then what you have to do to tweak that sequence to confuse it for another is change those sequences, that sequence in a time average sense, by epsilon. So for example, if you're looking at flipping coins with bias P and flipping coins with bias Q, and you want this distance between the two of them, you have to go into one that's got a relative frequency P of heads and change enough of those heads to make it Q. And the d-bar distance in that case is magnitude P minus Q. So it gives you what you'd sort of expect. So that is what makes it relevant for information theory and anything else which is really built on the ergodic theorem. Because you have to go in and tweak that stuff to, if the typical sequences of the two different sources differ by that amount, that's what the distance is. This is one that it's not of great interest to me, but the ergodic theorists like it. If you take the class of all mixing Markov processes, those are stationary, mixing stationary Markov processes, those are stationary and ergodic. And then if you add to that all of the d-bar limits of those things, that is the closure under the d-bar distance, you get the class of all B processes. And that's one of the characterizations of the class of B processes. So it's everything you can approximate in this particularly strong sense by something that's Markov. Entropy is continuous with respect to the Ornstein distance, d-bar 0. If you're dealing with independent processes, then all you have to do is a single letter characterization and match the marginals. We will take advantage of that. This one, it's not terribly well known, but if you look between two Gaussian random processes that are IID and have, oh, pardon me, I'm getting ahead of myself. I'm talking about the one on the next. That's what happens when you hurry. This is well known and old. Look at two Gaussian random variables and ask what their d-bar distance with respect to squared error is. It looks like this. And I wrote it because this is kind of interesting. It tells you one way to construct those joint distributions. Generate a uniform random variable, and then use that to separately, using the CDF trick, get your two marginals. And that turns out to be the optimal thing. Just compute the squared error and you've got it. One of the sad points in my life was discovering there's no n-dimensional version of that. Only works for 1D. If you deal with Hamming distance, you essentially get the variational or distribution distance of the PMFs. That's used a lot in ergodic theory. And this was the one I was starting to talk about. If you have two Gaussian random processes and you know their power spectral densities, then the d-bar distance is exactly that thing on the right. So it's a little odd. It's an L2 distance squared between the square roots of the spectral densities. And that actually is a lower bound to anything that's got those power spectral densities. Whew. Okay. That's part 2, so I'll stop there. And I didn't even need the 5 minutes. Okay, so I'll see you after. I had some good ones during the break.
I was wondering if there's a restriction on like looking forward in time or backwards in time. One place you define the memory, somewhere else it seemed like it could be anything.
When we're dealing with the theory and worrying about isomorphisms, it has to be unlimited. Because the isomorphisms may not be practical. In fact, people have worked very hard to build very simple ones. It's like Shannon, they tell you you can do it, but they don't tell you how. The infinite memory, people have pointed out, is unphysical, but then the little Gauss autoregressive shows you an example where, it's FIR filters. Anything that has feedback in it is going to have infinite memory. And that's an approximation people accept all the time. When I'm doing my optima, I'm allowing infinite memory. Unlike
non-causal infinite memory, right?
Well, it can be non-causal, yeah. Although when I construct all those isomorphisms I constructed, that I showed you in those examples from the coin flips, were causal. So obviously that's what you'd like to have if there's a hope of making it practical. When you're doing the optimum, anything's allowed. And the big difference between this and Shannon is you sort of pick a block length and then you try to find the best of the block length and you look at bigger and bigger. But you don't optimize over infinite length block codes because they make no sense. Here the optimization is over infinite window size, but they're just mapping into one symbol at a time, so that's perfectly well defined. And there are theorems which say if you can do something with an infinite window size, you can use a finite size and get arbitrarily close to that. So then you lose the perfect isomorphism, but you get an epsilon. And that's sort of the practical part is, okay, what can you do with things that you can actually put on a computer and simulate? And that's what I'll end up talking about, is actual source codes that are really based on a lot of these ideas. The other thing that was pointed out in the break that was very good was, why not the relative entropy instead of the distortion measures that I'm talking about? And I think the two reasons are, one, relative entropy works if you have absolute continuity between the two distributions. That means they're either both PMS or they're both PDFs. I've got a situation where I almost always have one's a PDF and the other's a PMF. And then relative entropy is no help. So it doesn't work there. The other fact is that I'm trying, when I get to Shannon, which we're about to start with, I'm trying to minimize an average distortion. And I'd like to have a metric on processes that captures that distortion, so that I'm sure if processes are close in that metric, then the average distortion between them in squared error or Hamming distance is also going to be small. Now the two are related, but the relations are only known for very narrow cases, and they're very difficult. In fact, now that I am half retired, I'm officially emeritus as of last month, but recalled at half-time. This is something I want to spend more time learning about, because there is a fascinating result that is used by other information theories, due to Kati Martin in Hungary, that shows that you can overbound the Ornstein d-bar distance by a relative entropy. And I've used that in some of the work. It's buried, I won't be explicitly going through here. It only works when one of the two processes is IID. So it's not as general as one would like. And there are similar results for squared error by Talleyrand. And these come up in an area of measure concentration that Sriram knows a lot about, but I know minimally about and clearly have to learn about. So I'm not trying to denigrate relative entropy. I think it's extremely important. I use it all the time. It's just not the process metric that's most handy here. Okay, so let me begin. Any other questions? Those were the two good ones from the two best ones from the break. Now Shannon comes back in, and while there's a lot written on the slide, the basic idea is that first step is to find mutual information and mutual information rate. And just as Kolmogorov did for entropy, Kolmogorov, Pinsker, Dobrushin, and others did for mutual information. And it's the extension from the case we know about where it's either a PMF or a PDF, and the limits are all nice. And the basic idea here is we've got a pair process, as we've talked about before. If the alphabets are discrete, one way to write it, there are lots of ways, it's just as this, the sum of the two marginal entropies minus the joint. And the key point is that this difference on the right is going to be non-negative because it's a conditional entropy, and that means that the entropy of the mutual information is bound above by the entropy of either side. And that's what's critical. And it's easy to show when we're dealing with the usual finite alphabet case. When we don't go with the finite alphabet case, we do the same thing that we did with the entropy. We take a supremum over all quantizers, that should be Q and R, quantizers over one and the other side. And then that will be less than the entropy, just because if you look at the finite result, remember the entropy is a supremum over quantizers as well, and you're just using the, you're just using quantization in the finite alphabet. If that's a supremum over all possible, it's going to be bigger than what this is with all possible quantization. And the bottom line is entropy overbounds mutual information. So in the finite case, trivial. In the general case, it works because you quantize into the finite case and take a suit. Information rate, again with entropy, you don't quantize and then take, pardon me, you don't take the limit and then quantize. It's the restart. Okay. You don't first quantize and take the limit. You take the limit and then you quantize. you want to use the definition for entropy rate and mutual information rate will be most basic for the finite case, and then you take the supremum when you quantize the processes. So here what you do is the mutual information for a pair measure is, down here is the supremum over all possible quantizers, and you can really do that over sliding block codes with finite alphabets or quantizers on single letters. Those all turn out to be the same, and whichever way you do, it's overbound by the entropy. Okay, this is what you should take away from this slide, regardless of how deep the understanding. It's obvious for the discrete case, and it's true if you use the general definitions of mutual information rate. Okay, so now we're getting even closer to Shannon. If you take that equality that I showed you before, where I argued that the distance, my process distance, to the class of all things I could get by coding coin flips if r is equal to 1, and I showed you that that was actually the infimum of the distance to the nearest process in the class of all stationary and ergodic processes that have that entropy constraint. That came from C9. And then I'm just going to do the infimum that defines the d bar, so I can separate these two things out. Here's the infimum defining the d bar. It's over joint that give me those marginals, and I'm now taking an infimum over all of the marginals with constrained entropy. And that's exactly the same as taking the infimum over all joint distributions, such that the y part has the constrained entropy. And here's the average distortion, because everything's stationary and it's simple. Now Shannon enters really simply. I know that h overbounds I. So this has to be bound below by the infimum over all pair processes that agree with my source, that's fixed, and have mutual information rate rather than entropy rate less than r. Because if the entropy rate is less than r, so is the mutual information rate. This is a more general, it's a looser condition, an infimum over a bigger set, I have to get a lower bound. Now you may not recognize this because it's not the way it's usually defined, but this is exactly the process version of the Shannon distortion rate function, which if you've seen any source coding at all, is usually, if it's a distortion rate, it's an infimum over all joint that imply the source, or equivalently you could say over all conditionals of y given the source. This is actually easier to deal with and write. Of the average distortion, it's the dual, as I'll write down formally, the rate distortion function, where instead you will constrain the distortion and try and minimize the rate. The big difference here is I went from my previous case of constraining entropy, which there are a lot of justifications for, and I loosened the requirement using mutual information. And now, as I'll make a little bit more careful shortly, this turns out to be the Shannon distortion rate function, which is the first connection with information theory. It's basically saying that my original question of how good a fate can I get is find the distortion rate function for your source at that rate. Shannon says you can do no better than that, and so now the obvious question is, thinking as a Shannon theorist, can you do that well? Is that inequality actually an equality? Okay, so top part is that's not the usual definition you'll see of rate distortion or distortion rate functions. People often see them in all elementary courses only for IID. If they see them more generally, they see them as a finite order distortion rate function, and then you take a limit. And I'll write that all down, and I'll just mention right now that yes, they turn out to be exactly the same thing. One of the people involved in first showing that, by the way, was Kathy Martin. She's been involved in lots of this stuff. Rate distortion function, why deal with two of these things? Rate distortion usually ends up being the best way to look at actually evaluating them and bounding these things. But the distortion rate actually is a better fit to the compression problem will be set up here. But they're absolutely equivalent, they're inverse, they're duals. So I've already asked the other two questions, so moving on. Okay, another page full of equations. The top two are the process definitions. You optimize over all stationary joint processes that imply the source and constrain either distortion and rate, minimize the other. And then here are the traditional versions. And what I've done to try and differentiate them is I just put the subscript X on the process version, and I didn't on the other version. All right. The theorem is that those are both the same. And while I won't do the proof, and I won't try and spout that back to you, the basic idea behind the proof is that if you have a process, you have all these finite order distributions. So you can use those distributions, which will turn out to give you a reasonable information. Let's say you're doing distortion rate functions, so you're constraining the rate. They'll have pretty close to the constrained rate, and they'll have some distortion. And that distortion can be no better than what you get if you optimize for that vector size, which would be the d sub n. So if I give you the process, it will give you the traditional version. It can't do any better than the traditional version. So if I have a process, I can get vectors. On the other side, if I do the traditional version and take Shannon, I get all these vector distributions. So what I'd like to do is show that can do no better than the process. And that's a little bit more delicate and interesting, because basically what I need to do is take those vector distributions for some fixed n and create a stationary process out of it. And knowing I might want to prove a coding theorem, and if you've read Gallagher's proof, you know that it would be really nice if you could actually get this process to be ergodic as well as just stationary. In fact, in his case, it's n-stationary. The problem is, how do I convert a block code into a stationary code so that if it's coding something that's ergodic, I'll get something that's ergodic out? And the way you do that is kind of clever. First, what you might expect doesn't work. If you take something that's n-stationary and you put in a random start, you get something that's stationary, but it's not ergodic. So you don't get a stationary code out of that. You do get a stationary process out of that. So you have to be a little bit more clever, but you want it to look like the blocks. So what the ergodic theorists did, and this is very much in Ornstein's construction, is you construct a stationary code as possible, as following. You will usually just send a long sequence of blocks. But every now and then, you can think that you're looking way back in the past for something that's asymptotically independent of right now and has really tiny probability. But when you see that sequence, instead of just continuing sending blocks, you put in a little bit of spacing, the length of which is determined by that event that you saw in the past. So what you're doing is you're putting in a little bit of random spacing, but the randomness is deterministically a function of the past of the source you're looking at. You can't use other randomness or it's not a stationary code. You've got some other beast, and then you'd have to worry about how to get a stationary code. So there are various ways of doing this. The best explanations are in the Shields and Neuhoff's paper on stationary codes. It tells you how to go from a block code into a stationary code, but that's the idea. So it's sort of constructive in that if you have a really good block code, it tells you how to build a stationary code. But it's ridiculous for complexity because you'd be sending these blocks for a long time and then just sort of staggering where the start is, which stationarizes the code. So I think I'll leave it at that. The slides, I think, will be posted so you can read what's there, but that's also pretty well discussed in the literature. So also, I made one mistake, and now I have to recover from that, so I'll apologize. What I just described worked, but I got ahead of myself. I'm talking about codes, and I'm still, which is the harder part. So I should have said that part later. Here I'm still talking about just probability measures. So that random spacing, I could have used separate randomness to get it here. I didn't have to depend on the source. So my apologies for thinking codes when I should have thought probability distributions, but the construction is the same and it's easier here. I construct the stationary ergodic distribution by just using the distribution for blocks, and then by putting in the random spacing. Okay. So, advantages of the traditional definitions, since I'm emphasizing the process ones, why? Well, one example is that you have algorithms to compute it. It's a convex optimization problem for any finite size vector. Blayhood and Rose both have numerical approaches to it. Gallagher and Cesar, Gallagher did it under more limited conditions and not as rigorous as Cesar did it. He did it quite definitely. If you're worried about the existence of these optimal probability distributions, Cesar is the place to look. The numerical optimization, I always mention Rose because there was a problem with Blayhood's original implementation when you're trying to look at continuous sources that caused some wrong results to get published when people were using the algorithm. And I'll say a little bit more about that later. So also there are lots of lower bounds. Basically, you'd want to use traditional to compute things. See, I don't think I'd mentioned that. And that's just that in the process definition, if I've got an ergodic source, I can optimize overall stationary and ergodic distributions and get the same things as I would have gotten if I optimized overall stationary and ergodic. Stationary general, stationary and ergodic particular, you get the same answer. That's very convenient when you're trying to prove coding theorems, which I won't be doing here. All right. I think that gets us through the math. We're now into Shannon's source coding, and just based on a conversation that I had, I think before last, at the pool with a student about finding PhD dissertations, I can't resist on this one. I found mine because I was talking to my master's thesis advisor, who was not my PhD advisor, and he suggested I read Shannon's 59 paper, and this was 1966. And he pointed out that nobody that he knew of had done anything with it since. And he thought it had a lot in it that could use expansion. I didn't know that Gallagher at the time was doing his rate distortion chapter. And I didn't know about Toby Berger, so there were people working on it, but there were certainly not many. And I actually, for sentimental reasons, kept my copy of the paper. That's the start of it. You can sort of see the notes through the years. But anyway, it was a very good pointer to a general area. He said nothing about what I should do specifically. That paper's still good reading. One bit of advice I give to anybody in an information theory school is go back and read the original Shannon. It's kind of good for a sanity check given all that's happened since. You know, all of the stuff I'm talking about is enormously complicated in comparison to the simplicity of what's there, and yet it's very clearly the inspiration for it. Okay, here's the source code. That's the Shannon mathematical theory of data compression. This is compression, not compressive. Compressive is often used to mean dimensionality reduction. The difference is bits. To do Shannon compression, you have to take whatever you've got to start with, which is typically continuous, or lots and lots and lots of bits, and map it into something with a relatively small number of bits. So the general picture could work for block or sliding block codes. I'm going to be looking at sliding block codes. So I'm going to take a source that I'm given, and it's going to be stationary and ergodic at least. And then I've got an encoder into a bit stream. I'm going to consider a 1 bit per sample case most of the time, because that's what I've done so far. And that bit stream is something I'd be interested in its behavior, and it's going to produce a reproduction. And the pi fg is the joint probability distribution from input to output that's induced by the source distribution and the code. So I get some average distortion, and if I'm talking about stationary codes, again, it's just a single letter, look at times 0, see what you get. So I know, because I've got this source going through an encoder into bits, so that middle thing has an entropy rate not greater than 1 bit per sample. A stationary encoding of that must have less than or equal to that entropy rate. So I know on the output, I've got to have something that's got an entropy rate that's no greater than 1 bit per sample here. And again, I could generalize to any integral number easy of bits in easy fashion. So now the question is, what's the best possible code for this? Well, I could have some class of codes, and the constraint is that they have to go through this bit pipe. And I could consider those that have alphabet size that has a log less than or equal to r. Well, up there I'm telling you r is 1, and so it's just going to be binary. And I could find the one that has the smallest average distortion. That's the distortion rate problem. And if you're dealing with block codes, it's something that's analogous, but you pick a block length and you deal with n-dimensional vectors. If I'm making stationary codes, I get to deal with this. This is called the operational distortion rate function because the entropy is the constraint. Okay, so now I can say a little bit more about comparing block and stationary codes. Block codes have the advantage that a whole lot is known about designing them. For example, transform codes, like wavelet codes and JPEG, and in some way you can think about compressive sensing followed by quantization as being a transform on the data to produce a set of coefficients that you actually then code. Vector quantization, that's just quantization of vectors. And a lot's known about how to design those codes. And there are a lot of very good codes and standardized codes. From a mathematical point of view, they don't preserve the properties that you would like. Even if you code something that's IID, you're going to lose the stationarity, ergodicity, etc. And so that can make proving things kind of difficult. Also, if you try and just take an easy method of stationarizing a block code by the random start that I mentioned before, the problem is that if you block things out, you can have some periodicities that are going to depend on edge effects. You can see them in old-fashioned transform codes. If I randomize the start, that's not going to make those effects go away. Right? The effects will still be there, it's just where they are located, you don't know. So this is really a fault. It's not something that you can easily fix. The other thing I said lots about already, that block codes aren't well defined for an infinite length. You can't talk about a limiting code. You can talk about as codes change, their distortion may be going to a limit, but there's not an actual code that they're converging to. Stationary codes, I've mentioned the first couple of things. The other's just a list of some standard techniques that are really stationary codes when you look at them. And that includes things like time-invariant convolutional codes. And if you look at the history and the coding theorems for convolutional codes, everybody always implements them in a time-invariant way. They use a fixed filter. All the theorems are random coding theorems where the coefficients in the convolutional code change. Because if you select those at random each time, the random coding argument works. So you've got a place where all the coding theorems really don't match the way it's actually implemented. I'm not claiming I can do that. I can get away from the time varying part, but I can't show you how things work when they're linear. That's still an open problem. However, convolutional codes, we saw one earlier and we'll see them again. So a wavelet also is another advantage. If you go back and talk to the people who were early in the wavelet compression revolution, you'll find that they didn't just take these enormous images and then take a block transform. They ran all their little filters through it. And as those filters ran through the image, they produced their coefficients. That is, locally in the image, their production of the wavelet coefficients was done by linear time-invariant filters sliding through the image. And then after that, they had some coding algorithm to convert them into bits. So it's a good model for the way wavelet codes behave. That's the way the originators did it, but lots of other people didn't do it. I got actually a very nice income once being an expert witness where somebody figured out, oh, you don't need to load the whole image in memory to do this sliding down, just enough for the filter lengths. And they patented it. They're basically suing everybody else who had wavelet codes. Okay, other point of sliding block codes is that it's very useful for mathematicians. And there are constructions, as I mentioned, going back and forth between block codes and stationary codes, which at least in theory tell you if you've got a good one of one kind, how to build of the other. And I have to say, historically, people understand how to build good block codes a whole lot better than they understand how to build good sliding block codes. So that's, I guess, why I'm interested in the latter. Okay, Shannon source coding theorem. The operational distortion rate function is the same as the Shannon distortion rate function, and that actually works for both block and sliding block codes. So you can't do any better than that. So we've seen that it's a lower bound for my fake problem, my simulation problem, but it actually gives you the source coding. So one would suspect that the two are related. And here, just positive coding theorem is hard but ingenious. It was Shannon's, the idea of choose your code randomly if it's, this is for block codes. And averaged over the performance, you will get good average over the ensemble of codes, you'll get good average distortion, so there's got to be one code in that ensemble that gets close to that average. And then the way the sliding block codes were proved is take the good block codes and construct sliding block codes from them. So unfortunately, nobody's ever found shortcuts to take advantage of the sliding block code structure. They wouldn't exist if it weren't for Shannon. Converse coding theorem is easy because if you look at the cascade of your encoder and decoder, that cascade is just a big stationary code. You know what the entropy constraint is. And so you go through essentially the same argument, and you can show that the operational distortion rate function is bound below by the Shannon. But the advantage is on the way of doing that, you have this infimum over processes with a constrained input and a constrained entropy, and that's this D bar thing that we had earlier. That was just the best fake that you could get with encodings of coin flips. So using the source coding theorem, I can observe that the best I could ever get in the fake process problem has to be equal to delta x, because delta x is equal to dx, and it's sandwiched in between the two. So I can actually achieve that lower bound I described, that the solution to what is the best fake process you can get from coin flips to a target process like Gaussian is exactly the distortion rate function of your target process evaluated at 1 bit per sample. So we now have an existence proof, if you like. I know they're the same, but I still don't know how to do it. So we have a solution, and I guess first, is there an intuition behind this? Is there some reason? And there are a few ways to argue it, but I'll give you the one that actually leads to some code structures, how I might argue it. Let's go back to what I saw long ago. Here's the shift register that I gave you in the simple example with a shift register of length 3. And by the way that was constructed was using that inverse CDF trick. But I didn't use that scrambling function to get this. I'll tell you in a few minutes what I did. I had to use something else to try and decorrelate to make the fake look as IID as I possibly could. I know I can't make it perfect because then it would be Gaussian, and it can't be. But let's just look at the simple code. I've got the shift register, I've got the states, I've got the outputs. Remember, that has to sit on the trellis, so there's just the picture that I saw before. So one thing I might do is if I want to code a Gaussian source, let's start at time 0. I want to find a really good fit to the output of my Gaussian source. Well, sitting on this trellis, I have things that I know if driven by something that's IID will produce a fake Gaussian. So why don't I just find the best path through the trellis that fits my source? All right, a minimum distortion search through a trellis is well known as the Viterbi algorithm. Okay, so I will take my fake process code. It's driven by bits. And then I will use a matched Viterbi algorithm to search my way through. And the blue and red is just pointing out that if it's blue, I'm going to put out a 1. If it's red, I'm going to put out a 0. So Viterbi algorithm is dynamic programming. It's a fast way to search through this. And these days with computer power, you can search for a really long way if you want. Now you might object Viterbi algorithm is a block code. So now in a way I'm cheating. I've got a sliding block decoder that's really short, but if I use a Viterbi algorithm, that looks like a block code. Right, there are two responses to that. All right, if you want to be mathematical and match this to the theorems, then take that block code you get from Viterbi, and nothing else is going to give you smaller sample average distortion than the Viterbi algorithm will give you for as long as you want to search. And now every now and then you put in a little bit of random spacing, depending on the path, in order to stationarize it. But the other thing is that a lot of applications, why bother? If what you want is a compressed version of something and you're going to play it out to somebody, take your entire sample sequence that you want to test this thing on. It could be millions long, run the Viterbi algorithm for the whole thing, and then just put out the bit stream from that. And that's actually, when I give you curves, we're doing that. So the argument is that that's not trivial complexity. Other people will beat us on that score. Can't argue with that. The Viterbi algorithm, the main issue is don't have too many states. So that means I don't want to let my shift register get too long. But again, with current computing power, you can have a shift register in a Viterbi algorithm of size 20. And that's an enormous code book. And code these things really nicely. So what I've tried to do here is there's not a theorem, although you can prove theorems to back up this idea. But what it tells you is if I do a good job of faking a process, producing a stationary and ergodic fake of my IID Gaussian target, then that could be a decoder in a source coding system, and the encoder does a minimum distortion match. And you can actually prove that then the source coding average distortion is going to be very close to whatever the d-bar distance is from your fake to the target process. So it's connecting d-bar with the distortion rate function. It very much depends on your having the same distortion measure. Squared error or having distortion in the two cases. Okay. Bit of a technical point that I'll just mention here because it does matter once. All of the theory of what I'm talking about now is assuming that we don't have enough rate on the channel to send the process perfectly. Causes a lot of mathematical problems when an isomorphism is actually possible and you could do it noiselessly. So I'm not quite as general as saying this works for all stationary and ergodic processes and rates. I'm looking at the rate distortion problem when I don't have enough rate to send the thing perfectly. So I just want to send it as well as I possibly can. Okay, so how do I get to G? I had some suggestions early on, but to get a little bit more careful there, I need to talk a little bit more about the rate distortion function and its evaluation. And what we'll end up with is fairly intuitive. In fact, I've had at least one conversation here where it was simply assumed to be the case. So I would classify the result that this will lead to as a folk theorem. But it actually isn't known in general, and its application is fairly narrow. So let me try and justify that. Okay, first, I've already said the rate distortion function is information theoretic optimization. Again, Gallagher and Cesar give you, it is Lagrangian or Kuhn-Tucker conditions in Gallagher. It's somewhat different in Cesar, but Cesars are very general. If you like to live in Polish spaces, complete separable metric spaces, instead of discrete spaces or Gaussian, you really need Cesar. IID source comes down to a single symbol minimization problem. You only have to look at the information at 1K, mutual information for individual samples. And that's really why we focus on IID in the coding results, is to take advantage of that. Also, it's one of the few cases where the process distortion rate function is well understood. That is, we actually know what the process is that achieves it. Cesar, Gallagher give conditions for achieving the nth order rate distortion function. They don't give conditions for achieving the process. But if the process is IID, their results tell you immediately you have distributions that actually achieve those infimum. The other case, by the way, where you know the process distribution is Gaussian. That you can find in nice closed form. Okay, so that's a few initial facts. Oh, and I should mention the thing in the title. I'm going to call a Shannon optimal distribution if you solve the information theoretic minimization and you actually have a distribution that solves it. That is, the infimum is a minimum. If you've got that distribution, that's the optimal distribution when we're dealing with mutual information. Very different from what the optimal code is. Question?
Is there a source channel version of this?
Is there a soup channel?
Source channel.
Source channel. Oh yes, for the process? Yes. That's in the references. A lot of this stuff is in my book, Entropy and Information Theory. This, I guess, is my commercial. The second edition just came out a few months ago. But it's also in lots of papers. And I did mention that the stationary codes all extend for channel coding. It's just, that's not my forte. Okay, point that if you've got IID, optimal distribution for n vectors is just the product distribution. Process optimal distribution is IID, with the Shannon one-dimensional scalar as the optimal distribution. This does play a critical role, and you can probably guess why. Again, people often assume this. When you actually build a code, and you actually look at the reproduction that comes out, you would suspect that if that's going to be a really good code near the Shannon distortion rate function, then your actual code ought to have a distribution that's not too far from the Shannon optimal. Okay, that's fairly intuitive, and actually I'll formalize that in a moment. Okay, what does Cesar say? Well, Cesar tells you these conditions for finding rate distortion for vectors. And there are other pretty general conditions. I will only consider real valued stuff. That's simple enough. But as I mentioned, they can be more general. And the basic thing that he showed that's of interest to me here is that if you have a sequence of distributions, which could come from anywhere, it could come from codes or pull them out of your hat. And if that sequence has one coordinate agreeing with your source, and the other coordinate is changing, but you know that the mutual informations are all constrained, which you'd expect for Shannon, and the limiting distortion looks like the distortion rate function. That is, if I can look at the sequence of distributions and they're getting better and better and better, then that sequence must converge. And it must converge to a solution of the Shannon rate distortion function. And in fact, under the condition where there's a unique solution to the rate distortion function, which there is in the Gaussian case, the sequence of distributions must converge to it. So if you ever need to know whether this distribution exists, check Cesar. He will tell you. At least if you're dealing with a finite dimensional vector or dealing with IID. But if you're in the real line with squared error, you're just fine. Now, here are a couple of side points that, again, I think several people who have published papers have been burned by. It turns out that you can prove a few things about this optimal distribution on the reproduction. And one of them is that if you're dealing with squared error and some source, there's something called the Shannon lower bound. And it's a fairly easy bound and fairly well known and often used. It turns out that if you actually hit the Shannon lower bound and you've got a continuous process, then your reproduction optimal distribution is going to be continuous. But if you don't hit the Shannon lower bound, Your optimal reproduction distribution is going to have finite support. It's going to be a PMF on a finite set. So that means with Gaussian, you're okay if you're looking at one-dimensional. You hit the Shannon lower bound. But if you look at the uniform distribution, you don't. And so you have, everything sits on a finite set. And that can be a small finite set, yeah? It's difficult. In Stephen Fick's thesis, he was a student of Newhoff's, and it's in Ken Rose's paper, which is in the references. And I played around with it a little bit to try and find a simple proof, and that's another thing that's sort of in the bag of things you could never find funding for, but it would sure be nice if somebody did. But the example of where that comes in is if you look at a uniform 0-1 source and take a rate 1, that is your optimal set. It's only 3 points. And this is what's wrong with Blayett. Blayett's algorithm is on a computer. You need a discrete source. So what does he do? He uniformly quantizes the source and then runs the finite algorithm and then gets an answer. The trouble is, if, for example, if he's dealing with this case, he might uniformly quantize the source, and he's hoping to be accurate, so he says he might have 10 or 24, some big number of quantization points. Forget what the number is, but he does. So he doesn't get these 3 points right. In fact, they're almost certainly not the points he's dealing with. So he gets a wrong answer, which then gets quoted by all kinds of people when they're trying to code the source. So Fick and Rose get it right, and you find out the rate distortion function is actually different in a non-trivial way from those that are reported in the literature. So one issue is that Rose's algorithm has as a claim, which there's a lot of numerical evidence for, it will give you what this finite set is. So that's good in a sense. It means that if you have a finite set, you've got a chance of getting a good distribution match using just coin flips, because it's discrete. But if it's Gaussian and you hit the rate distortion function, you're trying to match something continuous with something discrete, you're not going to do it. You're never going to get there, that is. You can get it close, but you can't actually get there. All right. Usually we start with talking about asymptotically optimal codes. All that means is if I have an optimum that's defined as an infimum over all codes, that means there exists a sequence of codes that get as close to the infimum as I would like. I'll call it optimal if it actually hits the infimum. And if it's optimal, then it's trivially asymptotically optimal. You just set all the nth codes to that optimal one. So my goal is now, what I had said somewhat earlier, I want to look at properties of codes that are optimal or asymptotically optimal. If I'm actually approaching the distortion rate function, what can I say about these codes? And if you're more awake than I am, you may remember I just had these Cesar results about if sequence of distributions behave in a certain way, they've got to be going to something. So I'm going to look at sequences of distributions as part of this. So the definition of asymptotically optimal just means eventually in the limit you get there. Okay, so I'm going to focus on the source coding problem rather than on the fake process coding problem. I've given you the definition of the two optimal, and I've argued that if you have one, you can pretty much construct the other. I've really only argued, no, that you can take the fake process and construct a good source code. I haven't really argued the other way, but we'll get there shortly. And in fact, that's one of the main points is, remember, we've got this binary process in between the encoder and the decoder. And so I will be making a rather strong claim about what that process has to look like. Okay, so this will be the general design approach. Find some properties good codes have to satisfy, and then very ad hoc, I admit it, try and construct codes that satisfy those properties. Plug them in, simulate, and see if they work. Either as fake processes using the decoder or as a source code. So I'd like to argue that this is an old idea in block source coding. One of the ways to design block source codes, if you've got the computer power and the patience and the interest, and there are some niche applications where this is possible, is to do an optimization problem where you fix the block length and you actually try and find the best code possible. The idea is known to most of you as k-means, which was published in '69. However, Lloyd in 1957 and even earlier, in 1956, it was done, proposed the basic idea, and it's a pretty natural one. Before I write the stuff, I'm not running behind. I think I'm okay. So this was just to warn you if I was in a panic now to get everything done, this would get skipped. But again, since a lot of you don't know much about source coding, it's worth giving you a couple of basic principles. So it's really Steinhaus that did it first. And the idea is you have an encoder and you have a decoder. And this is not a convex optimization problem to find the optimal encoder and decoder. If we did the Shannon distortion rate function and we constrained the mutual information, it is convex and we can solve that. If we're optimizing over two codes, it is not. So they realized in the 50s that if you fix one of those, let's say I fix the decoder, then it is a convex optimization to determine what the encoder is. And if I fix the encoder, it's a convex optimization to determine what the decoder is. So start with one and go back and forth, optimizing each for the other until things stop changing. Okay, if you know anything about optimization, you know it's pure luck if that gets you a global optimal or not. But you are guaranteed to get a local optimum, and it may be good. So the optimization properties here are basically optimizing the encoder for the decoder and vice versa. And if I'm given the decoder, think block codes now, not sliding block, that's just a whole bunch of reproduction code words. And basically I pick one of those, depending on my source block, and I send it or an index telling me where in memory to look to get it. If my goal is to minimize distortion, what I should do is just take my sequence on the input and find the best possible, in the sense of distortion, minimum distortion code word. All right, that's both intuitive and you can prove it rigorously in a moment. No code can do any better. So that's the optimal encoder. It's the nearest, just minimum distortion search. So if you go back to the case I described, that's the Viterbi algorithm. If you think of the thing as a giant block code that's locally sliding block. On the other hand, I can find the optimum decoder for a given encoder. And what I would do there is the decoder is going to take this index and it's got to produce something coming out. So if, for example, I'm dealing with squared error, what do I want? Well, I want to have something that's going to minimize the conditional expected distortion given the I. Okay, well that's the conditional expectation of the input vector given that I got I. That happens to be, if you do a little bit of geometric argument, the centroid, Euclidean centroid of all of the vectors that map into that index. So if the encoder is fixed, there's an optimal decoder and it's the centroid. And this algorithm, called Lloyd's algorithm, some people say Lloyd Max, but the way I just described it is the way Lloyd did it. Max did not do it that way. He did calculus and it doesn't extend to the vector case. Lloyd, what he did, everything extends quite easily. So given a starting code book, just iterate on the two, that's the Lloyd algorithm. The second thing I should add is this is also k-means, that is, it is in the 1950s, one of the earliest clustering, or now learning algorithms. So if you can, I think k-means has an admitted historically important part. People still use it all the time. This, Lloyd realized, extends to quite general distortion measures. All that you need is to be able to compute a centroid. And you could do that for a lot of things other than squared error. But squared error is all that I need to worry about. Okay, so those are optimality conditions, but admittedly, it's a little different. Here I'm trying to optimize for a fixed block length. And I'm not saying anything about getting near the distortion rate function, because I probably can't do it. Because Shannon just promises you can get there in the limit of enormous block length, and this is for finite block length. My definition for optimal in the stationary case is different. I have to actually get near Shannon. So that would be, take this and allow block lengths to grow without bound and just keep going. And eventually you can get near Shannon. Okay, back to stationary codes. That ends that detour. But it helps me make a couple of comments later. All right. Here's the first necessary condition. And these go back to, I think, 2008. So they're kind of old, and they shouldn't be surprising. The first one is, if you look at the process metric between the reproduction of the reproduction produced by a sequence of these asymptotically good codes and the original target, then if those codes are optimal, it's asymptotically optimal, it's got to be going to the distortion rate function. That's the whole point. They're getting better. So this is just reformulating something I said before. The other thing should also not be a surprise. It says the entropy rate at the reproduction better be the maximum you can give it, which is the 1 bit per sample or R bits per sample if you're being more general. Because if it's not, you're wasting information, and you probably won't do as well. So what that says is you basically want to get that really close to the maximum bit rate of the encoded process, and you want that to be getting near 1. Well, if the entropy rate of the process that's the encoded process is going to 1, that suggests it's starting to look like coin flips. In fact, that's where Kathy Martin comes in. You can use her inequality using relative entropy rate, convergence of the entropy, to prove that, in fact, the d bar from this encoded process and that of the coin flips, fair coin flips, has to be going to 0. So here are the coin flips again. You are basically forced to have coin flips in your noiseless channel if you're having nearly optimal performance overall. And that's another one of those folk theorems, which for stationary codes now has a rigorous demonstration. And it's, I think, perfectly intuitive. You would sort of expect that. So you can't really tell. These I won't go through in detail. I will point out they look just like the optimal quantization in PCM, scalar quantization, and there are vector quantization results that look very much like this. They talk about the moments, and basically you get reasonable things like the expectation of the reproduction. Well, the reproduction should be an unbiased estimator of the input. So that expectation should converge to the expectation of the input. You can write the variance of the ideal reproduction. It'll be the variance of the input minus the distortion rate function. And that's kind of interesting. Many people, myself included, in the early days of source coding, thought if we were trying to fake a process, what we wanted was the reproduction process to have the same moments. Okay, well the mean is true, but the variance is false. And really smart information theorists knew you shouldn't expect this, that it's going to be something that's reduced. So for example, if I've got a Gaussian process that's coming in and it's got variance sigma squared, I'm going to want something that is a fake Gaussian on output, but doesn't have variance sigma squared. It has this reduced variance. This is also very natural. It tells you that the error between the reproduction and the original should be orthogonal to the reproduction. And that's the orthogonality property, and it's basically linear estimation. This little signal processing comes up here. Okay, necessary condition 3. Now we're getting to the more interesting stuff. If we've got an IID process, and I've got an asymptotically optimal sequence of codes that give me some output marginal distribution, it must approach the Shannon optimal distribution, or a Shannon optimal distribution, V if it's unique, both in the sense of weak convergence and in the sense of transportation distance. So that's a claim for marginal distributions. Necessary condition 4. I don't need just for marginal. I need the same thing for finite dimensional. And this is just the statement that, again, it should be no surprise. You must be approaching the Shannon optimal for all possible n. Okay, the Shannon optimal, keep in mind, is the Gaussian marginal, and it's a product of Gaussians. So this says if you wanted a code that's asymptotically optimal, it's got to be approaching for all finite dimensions an IID Gaussian process. Well, if it were actually optimal, then it would have to be an IID Gaussian process. But that can't be. An IID Gaussian process has infinite entropy, and I've got at most 1 bit per sample. So the claim here is there is no optimal stationary code for Gaussian at 1 bit or any finite bit rate. You can get as close to it as you like, but you can never actually hit it, because this necessary condition will be violated. So it's a good thing to try and match up finite order. And the more that you can do that, the more you will fool people who are watching. But you can't hit it. So that basically just makes that precise. And a point here I should make is you don't get this conclusion unless you're looking at entropy rates. You can't get it if you just look at finite dimensional entropies. Because I can get infinite dimensional entropies for all possible finite values. But then when I look at the entropy rate, it's 1. Because the entropy, as I warned you, is not the limit of 1 over n h of x of n. Except when you've got finite alphabets and we don't. So there's no contradiction in having hn of xn hat be infinite for all values of n, and you have a bit rate of only 1 bit per sample. And that's a little mind-boggling. I think it takes a while to wrap one's brain about it. But it should come out as being intuitive. You cannot get IID Gaussian out of coin flips. But you can do a good job of faking it. This is just a minor point that your optimal reproduction should look at least uncorrelated. Maybe you can't get independent, but remember I showed you a fake process that got uncorrelated. That actually is not what I showed you, a good fake process to use. But it just demonstrated we can get Gaussian marginals and uncorrelated. So this is pretty much what I have said. Oh, the bottom point is a good one to make. I've been mostly looking at faking or coding for a Gaussian source. And there are cases where you maybe want to faking or coding a discrete source. For example, how well can you fake a fair toss of a die using only coin flips? Right? Well, it turns out, once again, if you use the Cesar results, and the key point here was done by Tomasz Linder, who's been a primary collaborator on all of this stuff, same conclusion holds. You can never actually hit an optimal. It will turn out that you get optimal probability distributions to actually give you the Shannon rate distortion function. But they have an output entropy strictly bigger than the 1 bit per sample I'm sending it. So I can never increase entropy by stationary coding. I'm doomed. You can approximate it very well. That brings up, it's not really the same stuff, but this issue of faking one process with another does have a long history in statistics and computer science. One of the classic cases being that if you have a fair coin, how would you simulate tossing a biased coin? I think it's called a bent coin problem. But they're not looking at stationary codings. They're looking at sending a bunch of flips of a fair coin in order that you can look at a whole bunch of coins to get out one that gives you a binary decision with the right probability. It's an interesting problem. Peter Elias did quite a bit on that, but it's not the same thing as this. Okay, so this is, I mentioned this once before, there's this sort of discontinuity. If you have an isomorphism, these wondrous codes exist that take you from one sequence into another in a stationary way and back with no loss. But once we've got distortion that's non-zero, or rate that's not enough, not the entropy of the process, then optimal codes no longer exist because of Shannon distortion rate function. So I don't understand that fully yet, but it's sort of an interesting anomaly. Okay, so now let's swing into the final topic. And here I am getting ad hoc. I have done a lot of hand waving to get away from doing theorems And now I have to admit, I have no proofs that the things I'm about to describe are optimal. And I have to admit also I'm tackling a problem which has been, one might think, beaten to death since source coding was first started. For example, who cares about how well you can code an IID Gaussian source? And so it's clearly sort of the information theorists who are trying to beat out their colleagues in a sort of contest over time and squeaking out that extra little bit that's at least past the computational uncertainty in the problem, or demonstrating that there is a way to design codes that's not quite the way people had thought before. But it's a much dealt with problem, and I can at least say, for the moment, I think we're closer to Shannon than anybody else we know about. And it hasn't been published yet, so we'll find out if somebody else is still playing with these problems soon. But it's on its way. It will be published fairly soon, and I think the results are kind of fun. Primarily, in our attitude was, we will not try and be practical and constrain complexity. We will use all of the computer power at the hands of my graduate student, Mark Mao, who did the computational stuff, and he works at Google. So you can see why we could look at really complex codes to see how this worked. And the difference is, every other coding technique we know of has found a plateau. As they get toward the limit of their complexity, things flatten off. They stop getting closer to Shannon. And we've not stopped up to the limit of our complexity. So I think there's some interesting facts. Okay, let me now try and knit this all together. So I'm going to try and find a code that satisfies the necessary conditions. In an ideal world, I could prove that it does. And it turns out I can prove, it's pretty obvious, actually, one of the key steps. The others I can't. We're still trying to do it. But we see that numerically they're very clearly satisfied. And there is one twist in this coding scheme that I've never seen before, and this is really due to Mark Mao, who makes the whole thing work. So let me do a little bit of, this is really reminder, so there's nothing new here, but just to go back to the beginning and to the fake processes I dealt with. I guess there is one thing new. I'm now not going to look at an infinite sequence because, as everybody knows, that's not practical. I'll look at a finite sequence, and I'll play the same game. If I have a shift register full of binary numbers, I can form a real number in the unit interval using exactly the formula that we did before. It is now a discrete uniform distribution, not a continuous uniform. However, it's easy to prove that as the shift register length gets long, that distribution converges weakly and in the transportation distance to the uniform distribution. You know, one's discrete, one's continuous, but it's converging in distribution. Okay, so once again, I will take my target, which I will now pick as the Shannon optimal distribution, because I know that's what I've got to get to if this thing is going to work. And I will drive it by my finite shift register length stuff, and hence, the inverse distribution operating on that finite length thing should converge to a Gaussian distribution. So that gets the marginals right. Let's see, anything else? But bottom line is, I already showed you that that gives you a really bad fake. And I showed you that scatter plot, and I think it's coming up almost next. It gets the marginal distribution right, but that's not enough. I need to get joint distributions right. So at least I should have the pairwise distribution right, and hopefully larger ones. That's what you actually get. That's the same thing I showed you before, and that's really bad. So I showed you one way to smear that out, but that way actually turned out, unfortunately, not to work very well. It's a very old way, and I like the analysis of it, but haven't found a way to make it work. But there's another way. And that's the following. And there's a key point I need to spend a little bit of time on. Take the shift register, and I want to do my mapping. What's in the shift register is a binary L tuple. Okay, it's one of this code book of 2 to the L binary L tuples. Select the partition permutation randomly once, then it's going to be fixed of that code book of all possible 2 to the LL tuples. Okay? It's not a permutation of the bits in the shift register. It's a permutation of the whole list of 2 to the L binary L tuples. So now what I'll do is I'll permute that code book, then turn it into a real number, and then take the inverse CDF. Okay, that's a block operation, but remember how I'm using it. It goes through the inverse CDF, I print out one symbol. Then I shift in a new bit, I have a new vector, I perform the same permutation on it, then convert it into something in the unit interval, and take the inverse CDF. So what that's doing is like my scrambling function, it's trying to scramble up the memory in the binary stuff and smear it out. And the standard, the observation is if I played the classic game in convolutional codes, for example, and allowed that permutation to change every time instant, I would have a coding theorem with no sweat. The hard part here is that we wanted to implement it with a fixed partition once, chosen at random. You just do it in that way. Okay, now this is my new sliding block code. It's the decoder and the source code, or you could use it for a simulator. So there's the picture, and I've got some length, which as I said, it's easy to consider up to length 20. And then I use the Viterbi algorithm, and there's the new scatter plot. Now that looks like a 2D Gaussian. I can't really do 3-dimensional plots, but I'll tell you more about higher dimensions in a bit. Admitting all the time, if you go to high enough dimension, you gotta be able to figure this out. Oh, one other analogy I forgot to make, and I don't think it's here, but I'll just throw it out. This is sort of like pseudo-random noise generators, where you have maybe this big seed, which you can use something random to generate, and then it starts driving something that prints out things that really look random for a very long time. And it eventually is periodic. So it's trying to fake a really random sequence. All right, here I have something similar. I don't have a seed, but I'm trying to fake a Gaussian process which has infinite entropy by dribbling bits into it. So I'm continually putting a small amount of real randomness into it to make it look like something that's really far more random. So I've never found any specific way to take advantage of that, but it's sort of analogous to a cryptographic problem of making things appear what they are not. All right, this is, the blue is a Gaussian CDF. The red shows what happens when you use a length 4 shift register, one bigger than the one I showed you way back at the start, and again at least once later. And it's using, it's modified to use this permutation, and it's a staircase, it looks not too badly. But when you get up to a length 8, that really looks Gaussian. So that says that the marginal condition is being satisfied. How about the joint? And here you can empirically show, we don't have theorems, that to the accuracy of the computer, that's uncorrelated. It's got a flat spectrum. So somebody looking at only the marginals in the second order would be fooled. And in fact, more is true if you look at the first order conditional probabilities for pairs, it really looks Gaussian too. The binary sequence that's actually going across the channel, it looks like IID coin flips. Well, if the binary channel process looks like IID coin flips going through this G, then it's no surprise that the output should be a good fake process, which was defined as the best you can do with IID binary into a stationary. So the fake and the coding problem are very much interrelated. The proof of that, by the way, is used with this specified Martin's inequality to show that the coded sequence actually approaches the coin flips as I had written up earlier. Okay, how does it perform in source coding and progression? All right, RP means random permutation, and the shift register length is listed along with it. So we went up to shift register length 28. Here is the rate distortion function, which is 6.02, and so the best with the long shift register was 5.95. And here are all the competition that we know about. Some fairly recent, this linear congruential stuff has some philosophical similarities to ours. And it specifically tried to use ideas from random number generators to generate the fake process. It's the closest that I know of in the literature. One of the best coding schemes out there is the trellis-coded quantization, but it's not really designed for Gaussian, it's designed for uniform, so I'll show you that next. So it's not that much of a surprise. So it's not that we beat everybody by huge amounts. I mean, it's on a dB scale fairly small, but still it shows that these things are on the right track, and they do compare with some very, very good schemes. And the older schemes compare worse than the newer schemes. This is basically a picture of taking the actual Gaussian IID source, and then what would happen if you coded it with just one bit with a scalar quantizer. That would be a really dumb fake. It's clearly binary, it's just using the optimal outputs. And then looking at what the fake Gaussian process does. And it does not a bad job. This is using the Viterbi algorithm to match. And again, it's both the source coding and the fake process, because the bits being sent are essentially coin flips. So this gives us a way to compare what the true Gaussian is with the one-bit Gaussian. So just visually, it's I think, an interesting picture. Merck results for the uniform, and this is where the trellis-coded quantization is specifically designed for that, using the trellis-coded modulation analogy. And it does plateau. You can keep increasing its quality, its complexity, and it does not keep improving. And we're doing not too badly in comparison with the rate distortion function on that, and again, beating the known competitors. There's always a problem when these results are reported in the data compression conference, and they're not yet in the information theory transactions. We haven't pulled out of the woods all of the people who may know things we haven't found in the literature. So hopefully that will come. Here's the fake uniform, with again, red is the real, green is the fake, and the blue is the dumb Lloyd or Lloyd Max quantizer. How about doing this for more general processes? And this is really new, but it's a good way to aim towards wrapping up. So I can't give you a lot of really solid stuff here. But all of the results we have that say that reproduction distributions of finite order must converge to Shannon, hold for the IID source. What if you get more general than IID? Well, the proofs don't quite work. You'd like to say something like the finite dimensional distributions converge to the finite dimensional distributions of the Shannon distortion rate function. But that would be, by most people's regards, the finite dimensional distributions for the finite order distortion rate function. But those block distributions might not be consistent with a process. So they're not the right thing. What you would really like is that those finite order distributions converge to the finite order distributions of the process definition, since you're after entropy rate and process in the limit. Those results don't exist. And while I can't say it's been thoroughly researched, and we certainly conjecture it's true, they haven't been proved yet. The only place we understand process rate distortion is Gaussian and IID. So that suggests one thing we should try is Gaussian. We know what the process is. We don't have a theorem telling us that's what we should go to, but we're pretty sure that's the case. So the student decided to look at a Gaussian that's been well studied. So best guess is Gauss autoregressive. We know all about the process distribution in that case. And picked a particularly simple one, which is a Gauss Markov, which cropped up fairly often in the literature, and try and code it using the same philosophy that I've described. Except how do you get this thing with memory? Well, there we do something that's natural. But there's a caveat. One thing is, autoregressive processes you get by putting them through a filter and driving them by something that's IID. So how about getting a fake IID Gaussian, driving the autoregressive filter, and getting our reproduction process from that? The caveat is that has been tried years ago and works really badly. But what this says is don't use the autoregressive filter of the original source. Find an autoregressive filter so that when you drive it by your fake process, you at least get the right spectral characteristics of the Shannon optimum. That is, don't try and copy the source. You can't do it. Try and copy the Shannon rate distortion function as best as we can with a simple filter. And here some interesting things happen. The asterisks are the results. The important one is the 1 bit per sample. Now the 1 bit per sample, we happen to actually hit that. Everybody else is pretty well above it. So this ad hoc code performed really well. The red curve is the rate distortion function for the autoregressive process that I wrote. And the asterisks show how you do at lower rates. And then the blue curve, what's that? Well, that's the rate distortion function of the input that's driving the autoregressive process. Again, some really old work proved that the rate distortion function of an autoregressive process is always bound below by the rate distortion function of the IID sequence that drives it. And the two are equal, provided that you're looking at big rate or small distortion. There's a magic point at which they hit. So it isn't just that this red thing is converging, it's actually hitting and joining it. So I and others have always thought, gee, when those two curves are equal, shouldn't you be able to design a smart code for the IID and just put it through the filter, and that would give you the smart code for the autoregressive? And I view this is just an observation that's within the last week in discussions with Mark. This sort of reinforces the fact that if you're operating in that region, doing what I said with the modification that it's got to be the autoregressive fit to the Shannon optimal, not to what we always thought, the original source itself, nobody's got that kind of performance on it. So here's a place where we're lacking the theory. Mark just handed in his thesis, so it's available as a PDF if anybody's interested. I should mention he's been a Google employee, so he's basically been given the free time to get his PhD, and so he will still have the free time to continue with some of this stuff. He'll graduate in a couple of weeks. So hopefully I still have a collaborator on this. I can't say it's a highly active area, or one that I would say is a really hot area to go into. But I find this fascinating, and I figure there's got to be reasons for this. And so it's certainly something I intend to continue playing with. Okay, some random closing observations. The first thing is, for a laugh, I told him, try tests for Gaussianity on this. Could our 1-bit fake Gaussian fool statistical test? And the answer is yes, if you run it with a Kolmogorov-Smirnov test of Gaussianity. The marginal and the conditional distributions up to a past of 3, or was it 4? 4. All flies Gaussian processes. I think that's kind of neat. All right, you have to go farther, and then you start discovering something's fishy. There's got to be dependence in here, and you can discuss it. Saki Weissman and Orlik developed some results for block codes that are similar to our convergence of distributions to optimal reproduction. And they're different because they're block codes and they're limiting results. And he doesn't look at the distribution. He takes short lengths and looks at sample average distributions. His results are for discrete, so they don't quite match these for continuous. And for IID, which is what ours are for, but he's also shown if you have something at least that's discrete and you hit the Shannon lower bound, the thing I mentioned before, then you get a convergence, this convergence of sample averages of coded reproductions to the Shannon optimal. So again, the Shannon lower bound crops up as sort of magical, and Saki and I are talking about this, how much in common and how different these things are. One of the reasons I talked about Lloyd was that when we're all done with this, I could go back and use learning. That is, I could use the Lloyd algorithm to optimize those shift register outputs. I gave you a formula for doing them that assumed I had an underlying distribution but didn't actually look at the data. If I now have vast amounts of data, I can simply run this each time, updating those centroids, running the Viterbi algorithm, updating the centroids, and use a Lloyd ID on this code structure. And what happens is no surprise. If you have a really short length, that helps. But if you get up to length 8 or so, it doesn't help at all. There's no point in looking at your training set and risking matching your sequence too much to what's going on in the training set. But it was worth the effort to try. Just, again, I have to admit, there's no easy way to get at those theorems of ergodic theory. There are books that have done yeoman's duty in trying to explain it, but it's heavily measure theoretic and advanced probability, and so it's not easy to go through. In my book, I make no attempt to prove the isomorphism theorem. I just try to explain it and then use it in ways that I've described here. The actual proofs of it, it's an amazing result, and it's very deep and it's very hard. One thing I may not have mentioned is when you use the Kolmogorov formulation and you talk about dynamical systems, this all works for continuous time systems and non-discrete alphabets. It's extremely general. So, for example, you can prove when continuous time processes are isomorphic, and it boils down to the same thing of equal entropy. There are continuous time B processes. That is also defined. The mismatch I just throw in because I haven't done a great job of justifying the importance of these particular process metrics. And their classic importance in information theory was from block coding, because you could show that if you design a code to be optimal for source X, and then you applied it to source Y, what was the possible change in average distortion? Well, it was bound above, at least when you use these metric qualities, by the distance, process distance between those two sources. So it was very nice to measure mismatch, and that gave an approach to universal codes, because you could design a code when you didn't know the distribution by take a huge space, maybe you constrain the correlation or the energy or something, and then you carve it up into pieces. You design a code for each piece, and then you simply look at the whole mess, find the best possible word and the best possible code. You send on your channel both which code you used and which code word within that code. So that gave a whole slew of universal coding theorems. So that process metric has cropped up in information theory in other ways 30 years ago. So there's nothing really new there. So in addition to Tomasz and Mark, whom I mentioned, the development of the early part of this stuff was really with Dave Newhoff, Paul Shields, and Don Ornstein. So a lot of them is mixed up in this, but as I say, don't blame them if I've made any mistakes, especially when with an engineering background I start doing interpretations. The rest of the pages you can see on the slides when they get posted, or I can send you a PDF. They're just a list of few pages of references that I consider useful. And with that, thank you very much for attending and getting up so early. It's been a pleasure.
questions? Any questions?
This would work for diffusion.
The basic theory will, and the trouble with the diffusion is if you get into things like the Weir process, the process itself is not stationary. So you have to deal with the increments. So I'm guessing that would all go through and somebody's done it. So they're about it for a